Hello. This is the last of the review sections from chapter 1, which is a prerequisite chapter. Section 1.6, which is rational expressions. We'll look at simplifying, multiplying, dividing, adding, subtracting, and simplifying more complicated looking rational expressions. This is from the OpenStax College Algebra 2nd edition. You can find a download to that book in the description. It's open source and free. That's why I'm using it. I'm using it as a kind of guide to go through this college algebra lectures. So lectures 1 through 7, which you could find in the playlist, the college algebra lectures, are all review. So if you're going to a college algebra course and you want to look at some stuff that you need to know for college algebra, this is the lectures 1 through 7 will help you with that. It's a review. The next lecture will get into the actual beginning of a college algebra lecture, or college algebra course lecture. We are going to look today at rational expressions. What is a rational expression? That's where we're going to start. So what is a rational expression? Let me say the word rational. Not to be confused with rational numbers, but in the same context, it's a fraction. Rational, we think of as a fraction. So it is like a rational number in that it can be expressed as a fraction, but where they differ is that a rational expression is essentially a polynomial fraction. Now it could have a polynomial on top and a polynomial on bottom. Now we think of constants as a polynomial if we think of it as being some number, say 2, where there's x to the 0, and say 3y squared. This is a rational expression. There's a polynomial on top and a polynomial on the bottom. So both numerator and denominator will have fractions. Students generally do not like fractions of any kind. So this is always a good review area for college algebra students. Even if you're in the course and you're doing well and you need some help with the rational expressions, this would be a good video to look at. Our first example is x minus 6 and x squared minus 36. This is a rational expression. So the first thing we want to do is simplify rational expressions. So how will we simplify something like this? Well, the technique is to factor and cancel when possible. So review factoring, if you haven't already and need a review. I will put the link to the lecture somewhere above or below down there. So we want to factor the top and bottom if possible, and then cancel what can be canceled. And that will be how we simplify this. So I'm going to look at this. And we have, I'm just going to write x minus 6. Now I need two binomials that multiply. They can be x squared minus 36. We know that this is a perfect square. X squared and 36 are both x and 6. Again, in our review of the lecture on factoring, we'll give a technique of how to do that. So now we cancel. I see that there's a x minus 6 and an x minus 6. So this is equal to 1 over x plus 6. So that's simplification. If this is unclear, think of a fraction, something like this. Now, I can break that up into its factorization. 4 I can write as 2 times 2, and 8 I can write as 2 times 2 times 2. So now I can cancel the like terms, and we're left with 1 over 2. The same will be true of rational expressions. We can cancel once we factor. So again, lecture 6 will be factoring review. Let's look at how to multiply rational expressions. As you can probably tell at this point, algebra, college level algebra, high school level algebra, all build upon each other. So we're using a lot of concepts we went through in lectures 1 through 6. This will be no different. When we multiply polynomials, we want to be sure that we know how to. So look at some of those review lectures. So let's say we have a expression. We want to multiply it. So these are two expressions, x squared plus 11x plus 30 divided by x squared plus 5x plus 6 times x squared plus 7x plus 12 divided by x squared plus 8x plus 16. So we want to multiply this expression. Now we could just multiply it with the techniques that we learned in previous lectures, that we just distribute one term in, say, this term over the entire second polynomial and continually do that until each term has been distributed across the second polynomial, and do the same for the denominator. Now you can see that that would lead us to having 6 terms on top and 6 terms on bottom. No, 9 terms, sorry, 9 terms on top, 9 terms on bottom. So a good strategy here is to factor first. We factor the top and bottom of both of these expressions, we might be able to cancel stuff, and then we can multiply if we want. And when I say want, it's stylistic. So x squared plus 11x plus 30, we can factor two numbers that multiply that give me 30, that when I add them give me 11, which would be x plus 6, x plus 5. The denominator, two numbers that multiply that give me 6, that when I add them give me 5. That's x plus 2 and x plus 3. Put an equal sign. And then the x squared plus 7x plus 12, the same technique, two numbers that multiply that give me 12, that when I add them give me 7. 4 and 3 are good candidates. And x squared plus 8x plus 16. This is one of our forms from the factoring lecture, but you can see that we can factor this into x plus 4 times x plus 4. So if you're not convinced that this is the actual factorization, you could FOIL these back out and you'll get the original polynomials. So let's cancel. Let's first look at maybe a simple example using numbers of how you cancel stuff. So we had 2 times 2 and 2 times 2 times 2, which was 4 over 8. So let's say we have something like 2 over 5. Well, we cancel these guys. There isn't a 5 in the numerator of either expression. So I can cancel the 2 here with the 2 here, even though they're in different expressions, because it's being multiplied. So these two will cancel as well, and then this will become 1/5. Same thing applies here. If I have a term in the denominator of one expression and the same term in the numerator of the other expression, I can cancel. So that's why this x plus 3 cancels. X plus 4 will go away. And that's it. So multiplying through, these become 1, by the way, just in case you wonder what happens. Well, those become 1. And then we have x plus 5, then x plus 2, and x plus 4. So at the beginning of the example, I said that if we can multiply out or not. I'll leave it in factored form. But if you FOIL these, you'll get a polynomial over polynomial. But leaving it in factor form is generally a good idea. No sense of making more work unless you're trying to solve or do something else, leave in factor form. So that was multiplying rational expressions. What about dividing rational expressions? One question you might have is why do we start with multiplication and division and not do addition and subtraction? Addition and subtraction seem to be easy conceptually, but with polynomials, it's actually a little more difficult add and subtracting polynomials than it is to multiply and divide them. So that's why we start with the easier stuff. So if we need to do other things with the adding and subtracting, then we have a sort of a basis for multiplication and division. So we're looking at examples. I could write out sort of an abstract rule for these, but I think it's best to look at examples. Examples help us sort of apply. If you look at these as being algorithmic in some way, that if you have different polynomials, that you could sort of go through the process and not have too much of a hard time. So what we have here is 1 over x squared divided by x plus 1 over x. If I wrote this as a fraction, meaning if I have 1/2 divided by 1/4, I can write that as a division of fractions. Most people don't like to do that, and there's a reason. It's ugly. So this guy is 1 over x squared divided by x plus 1 divided by x. So this is ugly. And honestly, it's more difficult to handle. So there's a rule. If I have, let's say, a over b divided by x divided by y, and so I'm dividing these two fractions, I can write these as reciprocal multiplication. So I take the reciprocal of x over y, which is y over x. It's basically flipping it upside down. I think in a previous lecture, I spelled reciprocal wrong, and that's embarrassing, but made sure I spell it right this time. So with this polynomial expression, this rational expression, we're going to do the same thing. Instead of writing that ugly fraction on fraction, we have this becomes reciprocal multiplication. And so we can write division as multiplication. This just becomes, let's write it as a single fraction. So this is x squared, and this is x plus 1. Now, I have an x on top and an x squared on bottom. Essentially, that means that I can take, this is x1 minus 2. This is x negative 1. It's 1 over x. You don't need to do that little aside, but this is why it works. And again, review your exponent rules. I think that's lecture 3. So we can write this as x. Well, x cancels, and then we have 1x on the bottom. So this is 1 over x times x plus 1. So that's the division of those expressions. We get something a little bit easier to handle. So most times in these examples, I try to do something that's a little clear and then something that maybe looks a little uglier. Just to give us sort of different looks. So here is a rational expression. So we can handle this one of two ways. We could factor first and then write this as a reciprocal multiplication, or we can write it as reciprocal multiplication and factor. Doesn't really matter which order you're going to do this. I am going to write it as factorization first. Oops, I forgot this. All right, so I can write the numerator here. Again, the hard part seems to be in the factoring. So review that if you need. But here's our refactor. Divided by 3x to the fourth, x minus 2. This would be the AC method for the top, and the bottom I'm just using the what two numbers multiply give me 14. Then when I add them, give me positive 5. That would be x plus 7 and x minus 2. Okay, so that is the factorization. Now, let's write it as reciprocal multiplication. And remember, reciprocal is taking the second fraction, turning it upside down, and writing that as a multiplication. So the numerator becomes the denominator becomes the numerator. And then we have this. So again, the order in which you do this, there isn't order operations on reciprocal multiplication and factoring necessarily, so you can do whichever one you want first. I'm going to now cancel some stuff. You're going to see something amazing happen. So this ugly division is just equal to 1. Everything cancels, means that everything that cancels is replaced with 1. So 1 times 1 times 1 times 1, and so on is just 1. So if you ever need a really ugly way to write 1, write this expression, and you have a very ugly 1. Let's do another one that isn't 1. Let's use a different variable. Let's use y. So 3y squared minus 7y minus 6, 2y squared minus 3y minus 9 divided by y squared. Missing the button. Y squared plus y minus 2, 2y squared plus y minus 3. They're not necessarily looking at cases in these examples where something doesn't factor, because we want to get some examples where we know what to do with the factorization. Let's say that all 4 of these things were not factorable, then the division would become reciprocal multiplication. Then we can distribute like we learned in the multiplying polynomials lecture. But that would just give us some ugly long polynomial. So you don't necessarily want to do that, but if you wanted or had to, you could. So I've chosen factorization, polynomials that factor, just so we can sort of see the process here. So I'm going to factor these first. This becomes 3y plus 2, y minus 5. And this becomes y minus 3. And this becomes y minus 1. y plus 2, 2y plus 3, 1. Now, what should be somewhat obvious is that if I am now in a division and I want to cancel, it's best to do the reciprocal first before you start canceling stuff. Because remember, the division is going to complicate the cancelization. It's not numerator and denominator. So writing it as a reciprocal has to come before the cancellation, unless the cancellation occurs on the same expression, meaning I can't cancel this and this if they were the same. I couldn't do that, not in division. So write the reciprocal multiplication first and then cancel. Of course, when you factor the right and left, you can always immediately start writing it as reciprocal multiplication to save yourself a minute. I'm writing it as an illustration so that if you want to rewind the video, you kind of see what came before what. So recip, roll call. I always want to say recip as RICOL, which is not right. So now I can cancel. I can cancel across numerators and denominators. What else we got? Y. All right. So Y2. Well, this is a 3. Why did I write as at 5? My fault. So those cancel. Those all become 1s. And then we're left with 3y plus 2 and y plus 2. So my mistake here was writing this at 5. My chicken scratch sometimes confuses me. That should be a 3. This would be a 3. So those cancel. So the division leaves us with the expression 3y plus 2 divided by y plus 2. All right. So that's multiplying and dividing reciprocals. Or reciprocals, multiplying and dividing rational expressions. So now let's look at the more complicated adding and subtracting rational expressions. So let's remind ourselves that when we add fractions, say we have 1/2 plus 3/7, we don't just add the top and bottom. We need a common denominator. So to find a common denominator from 2 and 7, sometimes it's just easy to take the multiplication of 2 and 7. That's 14. So the common denominator will be 14. It's just a multiplication of the two denominators. And then I think about, what do I need to multiply the 1/2 by to get 14? Well, it's just the other denominator. And I'll write it like this. Now, what do I need to multiply 3/7 by to get a denominator of 14? Well, that's just 2. So doing the multiplication, 7 times 1 is 7, 14 plus 3 times 2 is 6, 7 times 2 is 14. Now this becomes a easier problem, right? Because we have a common denominator, which we write as 14, and then we add the numerator. So that becomes 13/14. So this is the exact same method we use for adding and subtracting polynomials. It's just harder and uglier. So let's do something simple first. So let's say we want to add this expression 4 divided by x, and we want to add it to 10 divided by y. So the common denominator here I'm just going to take the x and y and multiply them. So the common denominator will be x and y. x times y. So what do I need to multiply the first fraction by so I get an xy in the bottom? Well, I have to multiply top and bottom by y. And what do I need to multiply 10y by to get xy in the denominator? Well, again, that's going to be x over x. A legitimate question is, how can we multiply with this by y's and x's? Doesn't that change it? Well, remember that y divided by y is 1. And multiplying anything by 1, it just leaves itself. This is identity, right? This is from, I think, lecture 1 or 2. Everything has identity. So this becomes 4y divided by xy. Y times x is the same as x times y by commutativity. This is 10x over xy. So I can write this as a single denominator in a addition of the numerator. Now we can't add 4y and 10x because they are not like terms. And so that is the expression. So once we add, we get that. And we're done. So that wasn't too bad. These get progressively worse, unfortunately. Let's mix a variable in here. So let's say we have y plus 3 divided by y minus 2. And let's say we want to add that to y minus 3 over y plus 1. So what we've been doing essentially is taking, in the previous example, that was a common denominator, but it's also the least common denominator, meaning I'm not having extraneous terms in there. So the lowest common denominator, or least common denominator, in this case will also be the multiplication of y minus 2 and y plus 1. Just like our xy case, just like in the 1/2 3/7 case, we're just multiplying the denominators. This will always work. It's advantageous to find the least common because it will save you canceling in the result, but canceling is much easier, I think, than fussing around with the common denominators. But that's a choice, I suppose. So I need to multiply this fraction by y plus 1, top and bottom, to get the common denominator. And I'm putting parentheses around just so that we don't get confused. And then this guy needs a y minus 2 over y minus 2. So this becomes, on top, y plus 1 times y plus 3 plus y minus 3, y minus 2, all divided by the common denominator, which we said was going to be, I'll put it in this order, y plus 1, y minus 2. Let me scroll up a little. So let's multiply out the numerator just to see if there's things that cancel, if it's possible to refactor once we've multiplied. Let me put that down here. So I'm going to FOIL this, which gives us y squared plus 4y plus 3. We're going to add that to this, which is 4, or y squared, sorry, plus minus 5y plus 6. That's divided by y plus 1, y minus 2. Combine like terms, we have 2x squared, so write that as 2y squared. We have a y term and a y term, so 4 minus 5 becomes negative y. And then 3 plus 6 is 9. And then we're going to leave that over here. So does 2 squared minus y plus 9 factor? Nope. So we leave it at that. You could also leave it here. I think the multiplication and combining like terms makes it look a little bit better. But again, it's depending on what you need to do once you've added these two things. In a calculus class, might be more advantageous to leave things in factored form. Most people that take college algebra are doing it for some prereq for some other major. But if you're a math major or a STEM field and you need to take calculus, the college algebra course is essentially a toolbox for calculus. It allows you to do a lot of things a lot easier in calculus class. So that's multiplication, division, addition, and subtraction. The subtraction will work the same way. Now let's mix stuff up. Let's write it out first. Simplifying. The text I'm looking at uses the word complex, which doesn't mean complex in the sense of a plus bi. That's a complex number. It doesn't mean that. So simplifying complex expressions, what they mean is hard or ugly or difficult. That's what they mean. So don't confuse complex here with complex. So simplifying complex rational expressions means we're just going to look at expressions that are hard or appear hard, appear ugly. And to get us off on the ugly bat here, that made little sense. But I think you get what I meant. Y minus x, or sorry, x divided by y minus y divided by x divided by y. So there's a number of ways to start. I'm sure as a viewer of this video, you'd be like, why didn't you do this? It's going to be quicker and much easier. I like to add steps and make sure that the viewer, the student, the interested party can follow through and see what's happening. So I usually take the long way around. That's fine. But again, there's always a quicker way to do these things sometimes, but these steps are guaranteed to work. So what I'm going to do here is I'm going to add the top, right? So we have a subtraction. So I'm going to do the same thing where I have x and y as denominators. So I'm going to multiply the first term by y over y. Oh, no, x over x. Subtract that from y over x, and I need to multiply this by y over y. Now the common denominators are xy, so I'm going to write that as xy, and then we have xx, which is x squared, minus yy, which is y squared, divided by y. Not too bad. Still ugly. But remember, this is a division. This is x squared minus y squared divided by xy divided by y. So we can write this as a reciprocal multiplication where we have x squared minus y squared divided by xy times 1 over y. And now we just multiply the tops and the bottom. So x squared minus y squared times 1 is just x squared minus y squared. And the denominator is xy times y, which gives us xy squared. So this expression that we started with doesn't look that much better, but at least we don't have fraction, addition, subtraction on top, and then divided by some other variable. We have a single rational expression, which is a little bit easier. Yeah, so ugly. Let's do another ugly one. Three divided by x plus 1 plus 2 divided by x minus 1 divided by x minus 1, x plus 1. Pretty ugly, but same process. We're going to add the top. The least common denominator, if we're adding the top, is x plus 1, x minus 1. So let's just look at the top here. And then we'll add the denominator after. So to get the common here, I need to multiply the left fraction by x minus 1 times 3 over x plus 1 plus 2 x minus 1. So the right-hand side, I need to multiply the top and bottom by x plus 1, x plus 1. So this becomes 3x minus 1 plus 2x plus 1 divided by x minus 1, x plus 1. Again, there's an easy sort of way to think about this, to do the top and the bottom of this initial fraction, the larger fraction, and handle it all at once. But I'm doing this step by step so you get a better sense of what's happening. Now I'm going to look at the top here and see, do we want to simplify that? Well, let's not. Let's leave it as 3 times x minus 1 plus 2 times x plus 1, and then put this all under, or above rather, the x minus 1, x plus 1. And the reason we're doing that is because I see I have a lot of x plus 1s and x minus 1s here. So it's possible that there's some stuff that's going to cancel. So let's write this as reciprocal multiplication. That's x plus, well, should be x minus 1 plus 2 x plus 1 divided by x minus 1, x plus 1. So instead of dividing it by x minus 1 over x plus 1, we're going to flip it over. So this becomes x plus 1, x minus 1. Now this cancels. Now you would be tempted to cancel the x minus 1 with the x minus 1 on top, but remember that's an addition, so let's leave that alone. We have x minus 1 plus 2x plus 1 divided by x minus 1 squared. So now let's look at the top and see if we can reduce any. So we'll distribute the 3. We get 3x minus 3 plus 2x plus 2 over x plus, no, x minus 1 squared. So that's 5x minus 1 over x minus 1 squared. There is no other simplification here, so that's the final answer. So we took this really nasty looking expression and we made it into something a little more manageable. Now, I'm going to write down a really ugly looking thing. So x squared plus 7x plus 12 divided by x squared plus x minus 6. We'll say we'll divide that by 3x squared plus 19x minus 28 divided by 8x squared minus 4x minus 24. And we'll divide that by 2x squared plus x minus 3 divided by 3x squared plus 4x minus 7. That's an incredibly complicated looking thing, right? If I have 1 over x divided by 1 over y divided by 1 over z, what does that really look like? Well, 1 over x divided by 1 over y divided by 1 over z is a really ugly way to think about it. We're not going to do that, obviously, but you can see how if I wrote it that way, this would be a little bit unruly. So let's factor and see if we can cancel stuff in the expressions themselves before we do anything else. So that's a good strategy, right? We're going to look at each expression separately. So we can factor this between x plus 4 and then x plus 3 divided by x plus 3, x minus 2. Then we're going to do this guy, 3x plus 7, x plus 4. Two-step factorization. There's a like term here. It's 4. If I take 4 out, I'm left with 2x squared minus x minus 6. So that would leave us with 4 times 2x plus 3, x minus 2. So again, do your factorization review. We have a video on factoring, which would be a good resource. Let's factor these. 3, x minus 1, and then 3x plus 7, x minus 1. All right, so that is a little bit better because we see in the expressions themselves, we can cancel some stuff. These x minus 1s go away. So that will leave us with x plus 4 divided by x minus 2 divided by nothing canceled in this. So this ugly guy is going to stay complete. And this guy simplified a little bit too. Okay. So recall your order operations, lecture 1. I'm going to multiply and divide left to right. So let's do reciprocal multiplication on the left side. So we're going to do 4. I don't want to write that in different order. So we have 4, 2x plus 3, x minus 2 divided by 3x plus 7, x plus 4. And that's still being divided by 2x plus 3, 3x plus 7. So now I have reciprocal multiplication in the brackets here. So now I can cancel stuff. So this goes. This goes. And what we are left with then is 4, 2x plus 3 divided by 3x plus 7. Now let's write this as reciprocal multiplication. So 3x plus 7 on top, 2x plus 3 on the bottom. And then we notice that we have this nice cancellation. So this is actually just 4. So this ugly expression that we started with, where was it? Right here, is just 4. So if ever you want to write 4 in a really ugly way, you can write it this way. Okay, so that's it. That's all I wanted to cover. So let's say end. So the OpenStax text has the review. This chapter 1. This ends those chapter or those sections. So we are done. We will begin the actual part of the college algebra course in chapter 2. And we will start with equations and inequalities. So chapter, my pen is dying, I think. Chapter 2 will be equations and inequalities. I think the first section is on the Cartesian coordinate system or the rectangular coordinate system, the xy's. So that would be the first place we start. So I hope this review has been helpful. And I look forward to seeing you in the next lecture. It will be lecture 8. So like and subscribe if you can. Thanks for watching, and I hope you have a great night.